All right, so as I said, clustering is one of the classic unsupervised learning methods where I give you some data and your job is to just group it into different groups such that each group or objects within a group are similar. All right, so I gave you this example of magazine articles, but then we talked about one particular algorithm, which is kMeans, and I'll give you a demo of how it works. All right, so this is the algorithm. Don't worry about it right now. I'm going to give you the demo. Okay, let's go to the demo actually. All right, so this is one of the notebooks. So what I do here is I create some data, some sample data, which actually looks like those examples. So let's say this is my data. All right, so there are 4 types of points. uh, Now you notice that all of these points have different colors and shapes, but that is just for us. The clustering algorithm doesn't know these colors. If it knew the colors, then there's no clustering, right? Then you already know which points are together. So the clustering algorithm looks at it without any color, right? And its job is to actually color them, right? So all the red should be with one color, and the actual color doesn't matter, but they should all have the same color, right? So now in this workbook, I have a sort of a very naive implementation of kMeans, okay? So if you remember in kMeans, the first thing what we do is we specify how many clusters there are, all right? And that could be a problem in general, but for now, let us assume that somebody has told us that yes, there are only 4 clusters. So the first step is you randomly choose 4 centroids. Okay, we call them centroids or cluster centers or representative points. So you randomly choose these 4 points. Those 4 points need not be one of these points. They could be something else as well. All right, so you could just choose. You could choose this 4 points right here or here. Doesn't matter, right? So the first step is you choose. So these big blue dots here are the 4 points that I chose by doing this random permutation. Now in this case, I'm actually choosing 4 points from the data set itself. But in general, that might not be needed. You could choose any other points as well, right? So you can see that there are 4 points like this, right? Now here you will see this is a very artificially generated data set, which it's very nice in terms of clustering. There are 4 clusters, right? So a lot of these cluster centers already are making sense, right? And that could happen, right? So now what you do is, now this is where you do the clustering. So what you do in clustering, if you remember the algorithm earlier from last class, is that the first thing that you do is you compare every object to these centroids and find the closest centroid for every object. So for example, you would say that this object over here, its closest centroid is this one, right? And maybe all of the objects here have this as the closest centroid. Maybe these objects, some of them would have this as the closest centroid. Maybe this one has this as the closest centroid. And that is something that you can actually compute, right? So that is the first step. Then what you do is then you say, okay, so that gives you some kind of clustering, right? So all the points that consider this blue point as the closest centroid are one cluster and so on, right? So what you see here is interesting is that, of course, these two already are looking pretty nice. All of them have the same color. But these two, because of the way we chose the initial centroids, most of the points are getting assigned to this blue centroid over here, right? Some of the points over here are getting assigned to maybe this centroid, and some of the points over here are getting assigned to this other centroid. All right, so that is the next step. Then comes the third step, in which you recompute the centroids. So what happens now is, now you look at all of the points that belong to this centroid, right? And then you compute the centroid of those. Now centroid means just a mean value, right? So all of these points, what you do is you recompute the mean value and you get a new centroid. And what you see in this next plot is that that centroid has moved a little bit, right? Because they're all collectively saying that this should be the new centroid. And the same thing happens here. Interesting part is here, where because so many of these points were getting assigned to this centroid, the centroid itself will move here, right? And then you keep doing that. So every time you recompute centroids, now you go back and reassign points. So now I have recomputed the centroids, right? Now what will happen is that more of these points will get assigned to this centroid, right? This one, the one on the bottom. And so and this centroid would get all of these points. So slowly this centroid would start moving towards these points, and this like that. So that's the idea, that slowly it would arrange itself in a way that they correspond to the natural clusters. So this is basically this algorithm running. Each plot is one step of k-means, and here you see that by this step number 3, the algorithm has pretty much stabilized, right? You won't see much change after that. But here I'm forcing it to run many times, but you could easily compute a convergence criteria and stop at some point. Basically, the idea is that you keep checking, okay, how much are my centroids moving in each iteration? If they're not moving by much, then you stop, right? It's pretty easy. And the number of iterations that it would converge in would depend on what your initial centroids were, right? So for example, let me run it again, right? Okay. All right, so let's look at this guy, right? So here, all the initial centroids, 3 of them are in this small ball and 1 of them is here. So now let's try to run kmeans. And then what you'll see is that you would see a lot of motion going on even after that. In fact, in this example, this is pretty interesting, is that it actually did not converge to the right value, right? Which means that the choice of initial centroids is very important. Even for this very seemingly very easy problem, k-means could get stuck in what we call a local minima and not find the right answer. If you see here, right, at the end, it's calling this as one cluster, half of this as one cluster, half of this another cluster, and this one is okay, right? So this example itself sort of shows you the 2 times I ran it. Once it shows you how good it is, and once it shows you how susceptible it is to a wrong choice of centroid. All right. So that is the point. Any questions so far? Okay. All right. So this is the algorithm that I sort of described, right? Then there are many variants of k-means. So of course you can choose some other distance, right? For example, right now in this example I used Euclidean distance, which is just the square root of the norm. But in general, you can use something else as well. There are other distance measures that you can use. And whenever you choose another distance measure, you get a new clustering algorithm, right? The other thing is, how do you find the cluster center, right? So in this example, I used the mean of the values. If you see here, this is the recomputation of the centroids. I'm essentially taking all the points that belong to this cluster, any cluster, and then I compute the mean. But you can compute some other statistic as well. You can compute the median or something else, right? In fact, what will happen is that if your data is not vector data, right? If it's not a vector of some attributes, computing a mean is not possible, right? In that case, you could compute the median or middoid, and then that kind of algorithm is called k-middoid. So for example, if you're, let's say you're clustering some arbitrary objects, okay? And let's say you do have some distance measure, some kernel function that computes the distance between these objects. So you can do half of it, half of the algorithm, but when it comes to computing the centroid, that's the part where you get stuck, because you cannot compute the centroids of a few strings or some graphs, right? In that case, it's easy to compute the middoid. Middoid is the object which is closest to all of the other objects, right? So there you could do that. So k-middoid is also an interesting algorithm in that sense. All right. So then there is another issue with k-means. Sometimes this distance, the choice of distance metric would also matter, right? It might not happen. It might happen that in certain cases, especially when you are dealing with very high dimensional data, Euclidean distance might not be the best choice. So you might choose something else. But the problem is it's not clear which one to use, right? Another question that was raised in last class as well is, how do you choose k? How do I say that I want 4 clusters? What if in this algorithm, right, what if I had set k to be 15, right? Because I didn't know, right? I don't know the color, so so it would do something. So kMeans would always run whatever you give it, and it would find some clusters, and a lot of these clusters might not make sense at all, right? So that is the point. Something went horribly wrong in this one. Oh, I see. I think this one assumes that there were 4 clusters, that's why. But anyway, so the point is that the choice of k is not something that's intuitive to find. That is something you have to provide, right? But when you're dealing with very high, now in this case you could have done it because you can see the data, right? You can see there are 4 clusters, so it's easy. But when your data is in 50,000 dimensional space, then you don't know how to set the k, right? So in that case, what you do is you try different k's and you compute the quality of the clusters. So there is a measure to compute the quality of the cluster, which is this. Okay. So if you look at this is what we call the kMeans objective function. So kMeans objective function is a function of C. C is the collection of all your cluster centroids that you get from kMeans, and R, where R is the assignment matrix. R tells you which point belongs to which cluster. So basically, at the end of the clustering, you would have these two things, right? You know what are your centroids, and you also know which points belong to what centroids. So the objective function looks like this. You're essentially computing the distance of every point to its closest centroid, right? Or the assigned cluster centroid. And then you're essentially squaring it and summing it up, right? So this becomes an objective function. So you can choose different k's, different actually uppercase k. So you can run this algorithm for two clusters, k equal to 2. You can compute this. Then for 4, for 8, for 16, and you can draw a plot and then figure out, okay, which one is giving you the best answer, right? So this is kind of a similar approach to what we did for estimating the best lambda in whenever we do regularization, right? There is no direct way, there is no principled way to find it, so we do this trial and error, all right? But at least there is an objective function that you can track, right? So that helps. Any questions so far? Yes. So saying right, exactly. So this function, so the point is that this function would give minimum value if you're if you are finding exactly that many clusters as you have data object, which means that every data object is a cluster and it is the centroid of that, right? So then what will happen is that this would be 0 and everything will be 0. But then that is not a useful clustering. So the way, uh, so I mean, what you do is, so k-means, right? So as I said, what you do is you, let's do this. So you compute this j, which is essentially a function of c and r, but it depends on k, right? And this is k. So what will happen is that at some point this will be 0. When k is equal to n, then this error would be 0, and then some behavior would be like this, right? So then it's up to you, right? Because clustering is something that you do to explore the data, right? So it's then up to you to decide, okay, should I just set k here, because at this point the number of k is something that I could work with and the error is not too high. Because if you just go by minimization of the error, of course you would always end up here. So that's not the right approach. What you want to do is figure out at what k you can use the clustering, right? Because remember, now the clustering by itself will give you the assignments, but then you have to you have to then use it in some way, right? So for example, you might be trying to let's say you are let's take example of Wegmans, right? So let's say Wegmans is trying to analyze its customers based on their purchase history, right? And trying to identify what are the sort of groups in the customer database that they have, so that then they can target them with ads and everything, right? So what will happen is they can do clustering. They can represent each customer as some in some feature space and do clustering, right? And then they can draw this plot, right? However, then they have to figure out, okay, how many do they need, which is reasonable for their end goal, right? So in the end, they want to target them, right? So maybe having too many clusters might not make sense, right? Because then you're basically saying target each customer individually. Having too few clusters might not make sense, right? So there is some other function that would determine what is sort of a roughly optimal k, and then you can play around within that neighborhood to figure out which one should you choose. So the point being that it's not a very principled approach to figure out k. It's just it's trial and error, as well as using some other governing factor to choose k as well. So you can't, I mean, one thing I can tell you is that this clearly is not a good clustering, or not a useful clustering, right? So not, and this here where your cluster is 1 is also not a useful cluster, right? So then you have to basically play around in this boundary and find the best one. Any other questions? Okay, so let me go back here. See, as I said, J is the objective function, right? So J is a function of C and R. C is the cluster centers that you get, and R is just the cluster assignment matrix, which basically tells you which point is in what cluster, all right? Of course, there are some issues with clustering, as I said, right? Choosing the initial parameters is very important. We already saw one example. And typically there are many ways to find the initial centroid, some more smarter ways. So one of them is that instead of just picking randomly, what you do is you pick the first point randomly, then you choose the farthest point from this point, pick that as the second centroid, then you choose the third point, and so on. So it's not guaranteed to give you the best result, but it's a little more robust solution. Another solution is to try many clustering runs. So you try, okay, let's choose these 4, and then run clustering, compute my objective function, then choose some other 4. So at some point you would maybe hit the right answer, right? Any questions? Okay. Then, and as I said on Monday or on Wednesday, is that clustering is very powerful, right? So whenever you want to try out a clustering method, or if you have some data and you have to do clustering, first thing you should try is kMeans, and then go from there, right? Because it's a good baseline, and in many cases it works very well. A lot of time my students come and say, you know, I have this new clustering method, and then the first thing I ask them is, have you compared it with kMeans? Because in many cases kMeans works well, right? But then there are some weaknesses that we have seen, and some of them are choosing the k is not is always an issue, of course, right? Clustering also tends to find circular clusters. The reason being because it uses that Euclidean distance, right? Which means that if your clusters are, the natural clusters are like this elongated, sometimes it has trouble finding those, right? So for example, and you can try that using the notebook as well, is that if your data looks like this, there's a cluster like this. So let's say I give you this data, and let's say there's some space here. Now you can see that these two form two naturally distinct clusters, but clustering won't find them. If you run clustering, and even if you say find me 2 clusters, it would do something strange. It probably will find this as 1 and this as 1. So you can generate this data. This data is essentially, you can create two-dimensional Gaussians with non-zero covariance matrices of diagonal entries, and then you can try clustering method that I have given you, and you can sort of see that. All right, so that is another issue with clustering. Okay, and then there are some other issues that sort of, okay, that's you know, easy to understand. Now the one thing that I want to sort of focus on is that Clustering is an example of an algorithm which does hard clustering. What we mean by hard clustering is that every object gets assigned to one cluster, right? So if you look at this, right, this is the cluster assignment matrix. The output of k-means clustering is that R n k. So for a given data point n, only one of this would be 1 and everything else would be 0, which means that every data point would get one color, either red or green, blue or black, right? But in some cases, you might want to make it a little more probabilistic, which means that you might want to have overlapping clusters. What does that mean? That sometimes you might want to say that, okay, this point belongs to this and this cluster, all right? Or this point belongs to this cluster with probability 0.9 and this cluster 0.1. But clustering doesn't do that. Clustering is a hard clustering method, which means that what it says is that this point belongs to this cluster with probability 1 and everything else probability 0. So it's an absolute, it deals with absolutes like Sith lords. So that motivates us to understand probabilistic clustering, right? So probabilistic clustering, also known as soft clustering. So instead of hard, soft, which means that instead of assigning every point to one cluster, each data point can belong to multiple clusters with varying probabilities, and that's the important part, right? So in general, the probability of xi belonging to any cluster Cj will always be greater than 0. So it will never be equal to 0 for anything, right? On the other hand, for hard clustering, it's either 1 or 0, right? So that's the difference. So that motivates the next part of our syllabus that I'll move on to. So I'm going to conclude k-means here. So any questions about k-means? Fantastic. There will be one problem on actually for k-means, but in the next gradients quiz, because I didn't know if you would cover this today. Or is the second problem about k-means? What's that? Oh, you didn't get. I think it is still about support vector machines, right? Okay. The next quiz. All right. Good. So let's move on to the next thing, which is part E2, which is about latent variable models. All right. So what are latent variable models? So this is another example of unsupervised learning paradigm, right? And it actually subsumes clustering. So clustering is also one type of latent variable model. But the reason I introduced clustering first is that sort of sets the stage for general discussion, right? So the idea behind latent variable models is that, so you can think of it more from the perspective of generative processes, right? So we have looked at these distributions earlier, right? Remember the distributions that we looked at when we were doing probability or the statistical machine learning was that we had some x, right? And we assumed that x was being generated by some distribution whose parameters were given by theta, right? And the distribution essentially gave us some probability density function PDF of P, and then you could draw the samples from that, right? And then we looked at what we call maximum likelihood estimation, where we said that, okay, if I have some training data, right, but the training data was just bunch of observations, you can compute or learn this theta, right, using MLE. Then we also looked at introducing the prior, doing Bayesian estimation and whatnot, right? But the idea is that you can do this in general. So here you can think of theta as something that is hidden, right? We didn't know this theta, and given some examples x, we were able to learn this theta. So that is one process. But now let us look at a different process which we call two-step generative process. So here what we introduce is this notion of a hidden variable, something that you don't observe, but that is something that creates the observation, okay? So we observe something, but that is not what directly comes out from the distribution. So the idea is that the distribution, which is again parameterized by theta, generates a hidden variable, and then that hidden variable generates the observation. All right, so there are two distributions in this sense. There's one distribution which generates the hidden variable, and second distribution that generates what we observe given the hidden variable. So let's go back to let's see. Okay, there's an example, right? So remember that magazine example that I gave on Wednesday, right? So let's say there's an editor who's trying to create this next issue of Time, right? So, right. So let's say X denotes an article, right? So X is our article, which is a random variable. So this direct model that we have looked at so far says that we have some distribution theta, and then what that editor does is she just samples the article using that distribution, right? So let's say that distribution. Now this is a sort of a contrived example, but let's say what should I say? Let's say there are 10,000 types of articles that there can be, right? And you have a distribution over those, which means that you have 10,000 probabilities which all sum up to 1. And what the editor does is that if she has to create a magazine next issue, she would go to that distribution, right, and pick one out of that, right, by those probabilities. So it's quite likely that she will pick something that has the highest probability, but it's not guaranteed. It's a random variable, right? So that is the direct model. But the latent variable model, or the two-step process, is that she would first, so, so this model assumes that all those articles, right, those X's are actually generated from some topics. So there are some topics that generate these articles, all right? So what the editor does is that she actually samples a topic first, all right? So let's say there are 4 topics. So then there will be a magazine article, a distribution with 4 values. Right? So the direct model was where she goes into a room where she has a probability distribution over all X's. Let's say there are 1,000 magazine articles that there could be. So there's a distribution with 1,000 values, and she goes and she picks one article out of that using this distribution. Then she goes picks another. Let's say she wants 10 articles, so she'll sample this 10 times, and here is your distribution, right? But in the two-step process, what happens is we assume that there are 4 topics, just for example, and there is a distribution over these topics. So this is topic 1, topic 2, 3, 4. So these could be like sports, science, health, and business, right? And then once she chooses a topic, right, then she goes into one room which is specific to the topic, and then samples X out of that. So each topic, think of each topic having its own distribution over these X's. Right, this could be any shapes. So what she does is she first, let's call this topic Z, this random variable. So she first samples the topic, and then when she has the topic, then she goes to the corresponding room, right? And then she opens that room and samples X from that. So that is the two-step process, right? So that is essentially the idea behind a sort of a motivating example behind latent variable models, is that there is a hidden variable that generates what you observe. Because after that, when I read the article, I as a reader, when I read the article, I don't know what topic they came from, right? All I see are the X's, right? But what I would like to know is what were the Z's that created these X's. Okay, they could have come from the same topic, or they could have come from, so, but I don't know that. So in the generative process, what would have happened was that the editor would have gone and she would have picked one topic based on this distribution, right? So maybe she would have picked topic 1 first time, and then went to the topic 1 room, which is over here, and then picked first article. So that will be X1. Then again she would have picked the next topic. Maybe that was topic 1 again, and then she would have picked X2. Then maybe she would have picked topic 1 again, X3, and topic 4, and then X4, right? So these are what we call the Z's, right? These are the hidden variables that generated this data. Now I as a reader would only have access to this, right? But what I want to know is what were these hidden variables, or what were the z's, z1, z2, z3, z4, that actually generated this data. All right, and why I want to know that, we will come to that later. But this is basically the setting for latent variable modeling. You observe something, but you assume that these observations were not directly sampled from any distribution. Instead, all of these were actually generated by some hidden variable, and then those hidden variables were coming from some distribution. And all of this hidden variable stuff is unknown. So that's why we call it latent variable modeling. All right. So now you can think of clustering also as an example of a latent variable model, right? Because in clustering, you have some bunch of points, and what you assume is that each point is coming from one cluster, right? So that cluster ID is your hidden variable. You don't know what it is, right? And you want to infer that. So that's why I started from clustering, but in general, latent variable models can be anything. Any questions so far? Yes.
So let's say for the topic one, there are hidden variables
Uh-huh.
to using x1, x2, x3, x4 from topic one, like all the data points from the cluster, right?
Yeah, all the data points from that cluster, right? Right. Yeah. So that's the connection between latent variable model and cluster. All right, so this is sort of a more statistical introduction to latent variable modeling. So the idea is that you have some random variable x that you observe, but x actually depends on a hidden random variable, which is z, right? Z is generated using some distribution p of z that we don't know, and x is generated using px given z. All right, so this is a different distribution, right? Now in literature, you will find many examples of latent variable model, and the difference between all of them is that what is z, what is x, and so on. So for example, if you assume that your z is a categorical variable, which means that the hidden variable can take maybe 4 values, 5 values, right? In that case, when you do latent variable modeling, that becomes mixture model. That will be our next topic. That's why I have it in red, right? If you don't assume that z is is a categorical variable, if you assume that it can take any value, then it becomes what we call factor analysis. If you assume that z is a vector, x is a vector, then it becomes what we call a probabilistic principal component analysis, and we'll look at all of these. And if you consider z to be a multi-nully distribution, which means that it can take it's a vector instead of just a binary value, then this is also known as a latent Dirichlet allocation. So we'll look at some of these, but the thing that I want you to take from here is that there's a general topic of latent variable models, and this is sort of the general setting. All right, and then we make some restrictions on what x could be, like x could be a vector, x could be a scalar, x could be a categorical value, and we make some restriction on what z could be. We also make some assumptions about what p would be. So let's say you can assume that pz is just a Gaussian distribution or something, right? So each one of those choices would result in a different model, right? And in general, all of these are scattered across literature in statistics, in math, not in math, but statistics, machine learning, data mining. But this formulation kind of brings them all together. So that's why I want to start with this, right? In fact, you can also include clustering here as well. That's one type of clustering actually can be thought of as one type of mixture model. So we'll look at that next. All right. So I don't think I want to. Oh, same slide again. I don't want to go any more today. Any questions so far? Fantastic. All right. So I will see you on Monday. Thank you.